Today with the literature review.
All right, so these are the various elements that are required to design or to simulate the hydraulic fracturing. You need to a good picture about the geomechanics. Then you need to have the right selection of the fluids and the proppant at a particular reservoir temperature and pressure. Then you need to design the perforation strategy and the pumping schedule. The pumping schedule now is giving us an idea of how the pumping will take place. How long will the pumping take place? Which of the steps will be more longer than which and all of that. So it gives us a clear picture of how you intend to do that. But there are so many things that you have to be careful about. For example, we may not want to produce a frac that is in this case where it doesn't occupy the entire height of the reservoir. So if in the course of probably modeling or designing and your model or your design is wrong, at the end of the day, you may produce a frac that has maybe doesn't occupy the entire reservoir and it becomes a problem. If your height is wrong, at the end of the day, it becomes a problem. If your height is too large as compared to the reservoir, you may end up fracturing zones that are not oil field zones, and probably they are water field zones, and as a result of that, you have water influx now. You have water influx from this particular zone into the perforations. So you have to be very, very careful because you have to ensure that at the end of the day, your fracturing model has to give us a best picture of what we expect to happen. Then, what gives us the shape, the main thing that defines the shape of the reservoir is the stress. That's the shape of the fracture, sorry. The main thing that defines the shape of the fracture is the stress. Because normally when you produce you're pumping your fluid in this particular interval. If you look, for example, here, this stress here has a lower value. This is 3,500. The highest here is 5,000. If you are pumping at, let's say, 4,000, you are expecting that it is higher than this value but lower than this value. So you expect that it will fracture only this particular zone and the fracture will not penetrate into this other zone because the fracturing pressure is not higher than the fracture pressure of the material. So the pressure at which you're injecting the fluid is lower. At this particular level is lower than the fracture pressure of that particular rock, of that particular interval. So it's not going to fracture. So the fracture may confine itself only within this particular interval. But if you have a stress field like what we have in this case, there is no big difference between this value and this value. So if you're doing your hydraulic fracturing, you may end up with a situation that penetrates outside the reservoir into other zones. So understanding the geomechanical situation of the reservoir is of importance. Now, how do we build a geomechanical model with what we call the mechanical earth model, which is a 1D model? 1D model simply, one-dimensional model simply means that you don't see a three-dimensional picture of it. Like, for example, this is one dimension, this is one dimension model because it's just giving you how the stress is going to vary from top to down. That means what you are looking at, you are looking only at the thickness of the reservoir, but you don't look at the width and you don't look at the length of the reservoir and all of that. If you are having a picture that takes into consideration what happens with the length, width, and height, then that's a three-dimensional picture. But this one is just variation with depth. So this is a 1D model. So how can you easily build that model? The first thing first is there are two things that you need. You need a sonic lock and you need the density lock. This density lock will give us what we call the bulk density. For the sonic log, we have two sonic log. We have delta T shear and we have delta T compressional. Either you have delta T shear, delta T compressional, or you have the velocity of the compressional wave and the velocity of the shear wave. So all of these are input parameters. All of these are input parameters. So it simply means that if you probably want to design the geomechanical model of that particular interval to see how the fracturing will take place, you need just 3 logs. 1, 2, 3. Because most of the time, this is not what will be given. This is what will be given. Delta T shear and delta T compressional. So 1, 2, 3 is enough for you to build the model. It's enough for you to build a geomechanical model of that particular interval. So from there now, we can calculate the shear modulus. This formula can be used to estimate the shear modulus. The formula can be used to estimate the shear modulus, and then the Poisson ratio. I explained the Poisson ratio. I don't know, you can get me right?
Yes, I can get you.
All right. So I explained the Poisson ratio yesterday, and this is a formula that you can use. Remember that RV, this is RV, which is delta TS on delta T compressional. Then from there now, we can move now to dynamic Young modulus. We can use it because at that particular level, they are assuming that some kind of motion is going to take place during the fracturing. Motion is going to take place, or probably during the logging process, you're sending in waves into the formation. As the wave is moving into the formation, no matter how small the vibration is, at least a little vibration is going to take place. So that's why we call it the dynamic Young modulus. You can use that dynamic Young modulus now to now calculate what we call the static Young modulus. So you can use the dynamic Young modulus either to use this formula, or in this case, where porosity is needed, to calculate the static Young modulus. From that now, you can now calculate now the vertical stress, which is the weight of the overlying material, and that vertical stress is given as the overburden gradient, times the thickness. Then you have the pore pressure, which is given as the overburden pressure, the pore pressure gradient, the pore pressure gradient and the thickness. And then from there now, we can calculate the minimum horizontal stress, which is also called the closure stress. This is the stress that is trying to close up the fracture at the end of the day. After you have performed the fracture, this is the amount of stress. This formula can be used to calculate the amount of stress that will be applied in trying to close up that fracture. So this is actually a good picture of how to be a geomechanical model of that particular reservoir. So if we are talking of stress, this probably will be the main focus. Yeah, this vertical stress will be our main focus. All right. So now, how do you now model the reservoir? How do you model the reservoir? There are two types of model that we are going to explain here, which is mostly 2D model. We could have the 3D model, but most of the time, what will be used, the simplest case is the 2D model. You have the 2D model, you have the 3D model, and you have the pseudo 3D model. Those are the three types of model that we have. I mean, yeah, in some cases, you may also have the radial fracture model. Yes, there's another model which they call the radial fracture model. But what we are going to discuss more is the PKN model. That's the full meaning of it. That's the full meaning of the PKN. Then the KGD model. That's what we have. All of them are 2D model. All of them are 2D model. Now, for the various these two, we are going to explain this. Now, for the PKN model, that's a picture of the PKN model. What are the characteristics of the PKN model? You are assuming that you have a fixed fracture height. It has an elliptical cross section. It has an elliptical cross section and an elliptical shape. An elliptical cross section and elliptical shape. And then the fracture half length is greater than 3 times the fracture height. is greater than 3 times the fracture height. So this particular model is actually, let me see if we have that. I think, did I even mention? All right, these are the two types of model, right? This one is a PKN model. So this is a situation where the fracture half length is very long. It's longer than 3 times. It's longer than 3 times the fracture height. So these are the two. So it just simply looks like these two cases. So whichever model you use now will probably depend on your pre-analysis of what the rock types are, if you're dealing with soft rocks or hard rock. So for this case, it has an elliptical shape, elliptical cross-section, and the half length, the fracture half length is greater than the 3 times the fracture height. But in this case, which is a KGT model, we have the fixed fracture height, then we have the rectangular cross-section, then an elliptical shape. Then you realize that the fracture height is greater than, is far greater than the fracture half length. So I hope you now get the picture of the two. Yes.
Yeah, I get it.
Yeah, so these are the two models. So probably our essence now is going to be on the PKN model. So this is what you are going to probably explain more in your methodology, the PKN model. That's what, because that's probably what you're going to use. So I think if you look at the book, that book, you are going to get a good detail of how the PKN model slide you can have. You know that in your methodology, you don't write that much, right?
Yes, sir. Yes,
You don't
sir.
write much. You don't go and start explaining history under methodology. Methodology is
All
just
the
for you to identify what you are supposed to use. I am using this model. Like for example, we have talked about the objective. What did we say the objective were again?
we said the objectives were first to to evaluate the productivity of the well.
You did not write it down. The first, you have to be sequential. Methodology and methodology and objective has to be sequential. You start from the first things that are carried out, the last thing. You cannot go and you are talking of productivity when you have not yet fractured the well.
Yeah, that's true, sir.
And you cannot fracture the well if you have not modeled it, right? So you don't just go and you put objective anyhow. It has to be sequential. So the first objective is to model and design hydraulic fracturing.
Yes.
Are you okay with that?
Yes, of the yes, sir.
The second objective is to evaluate post-frac skin. To evaluate post-frac skin. So the skin is the skin value after the fracking. So to evaluate post-frac skin, and the last objective is to evaluate post-frac productivity.
Okay.
To evaluate post-frac productivity. So your first methodology has to be how to answer objective 1. How do I answer objective 1? How do I model and design hydraulic fracturing? Are you okay with that?
Yes, yes, sir.
Second method now will be how do you determine the post-frac skin? I think we have already talked about that, right?
Yes, yes.
Then how do you evaluate post-frac productivity? We have already talked, we have just mentioned a few about that, which I said it doesn't change the Darcy's law that much, right? But we are still going to have a session about post-frac productivity again, so that we add more flesh to it.
Yes, sir. Yes, sir.
All right. Yes, sir. So now, if you are choosing this model, this is actually the formula that is used to obtain the fracture half length. You have the Poisson ratio, you have the Young modulus, you have the injection rates, that's the injection flow rate, then you have the viscosity of the fluid, and then you have the fracture height, then you have the pumping time. You have the pumping time. So you can actually, from the model, you can actually estimate what the fracture half length will be and what the width of that fracture is going to be. So for the KGD model also, that's the formula that is used. So if you are using a PKN model, this formula is supposed to be part of your methodology after you have indicated this diagram, because this diagram definitely has to be something that you have to put there and try to explain how the model is. You don't need to mention this in your methodology because this one is not what you are going to use. You don't go and start mentioning things that you are going to use, that you're not going to use.
Yeah.
Are we okay with that?
Yes, sir. Yes, sir.
So for the design now, designing means that you have to plan the pumping schedule. That's the meaning of your design. So this is an example of a design. And this design is obtained from GUA, I think Petroleum Production Engineering, computer assisted approach. I don't know if you have this book. Hello?
Hello, sir. I can't get. Yeah. Okay, I didn't get you. You said the design is obtained from petroleum.
I'm asking if I say this particular pumping schedule is obtained from Petroleum Production Engineering. Do you have this book?
No, sir. I don't.
I think I'll send it to you. So this is an example how you have to design it, how you are going to pump, which time you're going to pump. God. My machine is showing low battery and there's no light. This Bamenda with issue of light there. So this is how a design looks like. You can actually get a picture of the design, right?
Yeah.
Because there are 3 stages.
Yes,
There
yes.
are about 4 stages in the in carrying and hydraulic fracturing. We have the part stage, you have the slurry stage, we have the flush stage, and then we have the shut-in period. So each of those ones now, the slurry stage could be at different stages, at different level. The slurry stage is where you are pumping a propant. Where you are pumping a propant. So it has a particular time schedule for each. And what type of fluid are you going to use? Are we okay with that? What is the propant concentration? What's the propant concentration? What's the slurry rate? At what rate are you going to do the pumping? And what is the propant type? So this is actually a picture of how the design looks like. That's why we are talking about objective 2 is to model and design. So you are supposed to give a picture of this type of design. I'm not saying that it should be exactly like this. When we go to the practical, we are going to see what design we can use. Are we okay with that?
Yes, sir. Yes, sir.
Yes, but so this is how your design is going to be like. So we are already arranging how your methodology should look like. So don't go and start asking me, sir, how will I write the methodology? I'm only telling you that the first aspect about the methodology is answering objective 1. You are looking at each of those objectives. What is the method that, forget about the fact that the software is doing the job. Assume that there is no software. Are you getting the point?
Yes, yes, sir.
This is the reason why you are giving the formulas. The software will give you all these values, but what formula is the software using to get those values? That is what is more important. Don't go and start saying that the software is doing the work. No. The software is doing the work, but the software is using a formula that has been embedded inside the software. Are you getting the point? Hello? Hello? Hello, Belov. All right. So from there now, you realize that when you look at the pumping schedule, there are different stages of slurry. And if you come here and you realize that they have different propant concentration. So you come here, you realize that this is the part stage, this is the part that goes in first, and then you have different levels of different propellant concentration. This one will definitely be a smaller size, this one be another smaller size, and then you're moving towards bigger size. So the propellants necessarily are not of the same size. You have smaller propellants that are first of all injected, then you have larger propellants that come after. So at the end of the day, this may be a simulation that you produce. You may produce this at the end of the day. So you see, this is what you're now going to see that, all right, this is a design, this is a simulation that I have produced at the end of the day.